Okay, so I'm going to talk about 400 gig optics this morning. As LJ was saying, we've been doing a lot of work. This has been a major lift for the industry, definitely for Cisco, on some of the challenges. So really I'm going to go through why we being driven and what we have to do to make this successful, and then what are some of the key enabling technologies that we've had to focus on, and then what that means in terms of solutions and what's actually happening beyond 400. So I don't think I need to spend a lot of time here, but we all know that the traffic pressure that's coming at us. We all know that the number of users are increasing, the speeds we're doing, and that's all pushing everything towards 400 gig. And as LJ said, this started actually quite a long time ago within Cisco, but also within the industry to solve it. Specifically to optics, if you go look at something like the Cisco VNI Cloud index that we do, if you do a breakdown of what's being used within where the interconnect is within the data center, a lot of, like 70% of the interconnect within the data center is just within the data center. And what that's doing is it's putting a huge amount of cost in the data center just from the interconnect. And the result of that means that we have this massive pressure on us to get the cost of optics down, because it's becoming more and more dominant in the cost of a deployment. So the challenge that makes this even worse is as we go faster and faster, the percentage of the cost of optics is greatly increasing as we go faster and faster. In the olden days, so, maybe back at 10 gig or something, the cost of optics was relatively minimal compared to the cost of the system. We had to use lots of ASICs, the hardware to cool everything. Everything was very expensive, and the optics was generally quite cheap. A lot of that was just because there was a lot of volume at the lower speeds. As we push up to the higher and higher speeds, stuff that LJ's been talking about, everything's getting integrated into the silicon. We got one chip on the board, and now we have surrounding that by multiple optics, and the optics are getting very, very hard to do. So we're seeing that percentage shift between the cost of the pluggable optics and the cost of the system itself has really kind of flipped as you go faster and faster. And that's putting a lot of pressure on us as people worrying about how to build the optics to make it as cheap as possible at these data rates. Okay, so that's kind of the cost challenge that we're dealing with here. The next challenge is when you go look at what's happening with 400 gig E specifically. If you look at the forecast, it's expected that the 400 gig E market is going to grow in the first 5 years of adoption to be 20x more than 100 gig did in the first 5 years of its adoption. And what's the nuance there is really there's multiple markets trying to adopt this at the same time. So back when 100 gig first came out, back in sort of 2010, it was really the service provider market was pushing, and it was growing very well for that market. And then the data center market really picked it up sort of 2016, and that's when the volumes really, really took off. Now, what's different in 400 gig E is all these markets are looking for the technology at the same time. And that's fundamentally the challenge here, is how do we make sure we are able to compact that sort of 6 years of maturity to get the cost down and the size down and the power down to make it ready to go day one. And that's the fundamental challenge of 400 gig E optics. So when I talk about optics, often I talk about client optics or DC optics. That's really the optics that goes inside the building. And then much more challenging optics is what we're often called line optics, long-haul optics, transport optics, which is really what you use to go sort of tens of kilometers, thousands of kilometers. And there's kind of differences between the two. Within the data center or for client optics, the fiber is very plentiful. So really we're just trying to go short distances. We can use direct-to-technology still today, but our figure of merit is really dollars per gigabit. How do we get the cost down? Whereas on the line side, the fiber is scarce. We're trying to go further. We're using much more complex technology known as coherent technology. And really that figure of merit is really dollars per gigabit kilometer. Just how far can we go? So what do we need to do? So how do we make 400 gig optics ready for the market? Really it's how can we get the cost of that optics down? So it's really built up from 4 different components. I'm going to dig into each one of those in the time I've got. So the first one is really we need to do some advanced integration Silicon photonics is the fundamental technology transition there. The second one is get everything into a single form factor. And the reason this is important is just from the use case, how people are using it. It's very important to get everyone using the same things and having it backwards compatible with what went before, but also getting all the volume onto a single thing. That's what drives the cost down. Third thing is we just have to speed the optics up. We have to get it going faster. And the technology I'll talk about is the 100 gigabit per second per lambda technology. And then finally, the intersection of bringing that line side optics, the long haul optics, into the same form factor as the client optics and getting the sort of 400 ZR technology to be pluggable with the same form factor as the short reach optics. Okay, so digging into that a little bit. So silicon photonics is a new technology. Well, it's not that new actually anymore, but it's sort of starting to hit mainstream now. This is basically reusing the CMOS technology that we use for all of our chips, but using it to control, generate optical signals. So silicon photonics allows you to basically couple light into it, allows you to guide the light through the waveguides. You can modulate the light, turning it on and off. You can detect the light, and you can put it very densely in the chip. Now, the key advantage here is you can do all that, which is great. It's low power, it's very fast, but you can scale it into a wafer process. So if you go over to the Cisco Live floor, you'll see a big wafer with one of these on it, and you can see all the different chips. But this wafer scale is really how you get the cost down. You're able to build hundreds and thousands of these at a single time, cut them up and put them in the module. So when you go and look at this, it's really you're building a transceiver in a chip. So here's a sort of cut-up example here where you can see a silicon photonic die. You can bond an electronic die on top of that. The laser goes on top of that, and really that hybrid integration is how you're going to be driving the cost down. A lot of it comes from this wafer scalability where you have the whole wafer, and again, it's highly automated. So if we go back and look at that picture we had before of the inner building stuff, the DC and client optics and the long haul, from a Cisco perspective, we've put a lot of focus on this. We've got actually 4 acquisitions over the last sort of 8 years where we've heavily invested on the silicon photonics technology with our Lightwire and Luxtera acquisitions, and we've heavily invested on the line side with our core optics and the Acacia acquisition that we just announced. And with the Acacia, we're bringing in the silicon photonics there, as well as the complex digital signal processing needed to be very successful in that technology. So this is all aimed at really getting that 400 gig cost of optics down as low as we can. So going back to the first thing, let's get into how do we get into a single form factor. The motivation for that is twofold. One is backwards compatibility. So if you have old systems, you can connect your old optics in. And the second one is really just to get the volume as high as you can. If everyone's building the same thing, that's where the cost comes down. So history, as I get older, I look back and I find nothing really new happens. It just happens with a different number in front of it. So when I look at the past, what did we do when we transitioned from 1 gig to 10 gig? We were using the SFP form factor. That was in high volume. When we went to 10 gig, we moved off into something called ZenPack. And as we got better at it and mature and volumes picked up, we had to get smaller and smaller, get the density up. And it basically worked its way around back into an SFP form factor. And we kind of did this little journey and back to it. Right? When we did the same transition from 40 gig to 100 gig, exactly the same scenario happened. We went from QSFP plus module, and then we went off into CFP and CFP2, and there was a little bump called CFP4, which the industry kind of ignored, but we came back to QSFP 28. And the reason we do this all the time is because getting it into the same form factor from a system perspective is what we want to do, the same number of ports, the same radix, and the backwards compatibility is actually very valuable because we find a lot of people will put the lower speed optics into the higher speed ports, especially at the beginning of an adoption cycle. So what was the challenge for 400 gig is how can we circumvent that, going around that circle again, because there's reasons why we do this. It's all about fitting the more challenging high-speed optics into that small form factor at the beginning is very hard to do. Trying to get the long-reach stuff in that small form factor is very hard to do. So a lot of time and effort has been put into for 400 gig, making sure that doesn't happen. All right, and so with 400 gig, the transition from 100 to 400, it's going to be the very first time that big transition step like this has happened, and we're not going to change the form factor fundamentally. So we have, as an industry, figured out how to stay in that QSFP DD, QSFP form factor. We call it QSFP DD for double density, and I'll talk about that. But fundamentally, this is the first time we'll be able to go everything from copper optics all the way up to long haul, all within this QSFP family. Those of you that are paying attention to this know there's another form factor out there, OSFP. For all intents and purposes, it's the same. It's a metal box which we fit optics into. It works. QSFP DD works. It's just a bit of a beta versus VHS thing going on right now. But fundamentally, the fact that we're able to pull off all the implementation in the DD, I don't really see a reason the market isn't going to adopt it. And we're not really having any customer interactions where people are asking for anything other than DD. So we go with that. What is QSFP DD optics? LJ had the slide before, but fundamentally it looks exactly the same as the QSFP 28 that is in high volume today. It's more power. As LJ said, the 400 gig is just fundamentally more power. So the big challenge around this optics is how do we cool it? And that's a system problem to solve. And I'll talk about that. We're able to get all the reaches in it from copper all the way up to the coherent. And we're able to fit the 36 ports across the faceplate into that. And that's one of the key things that, when LJ's talking about the architecture of the line cards, and again, the backwards compatibility, and it's all compatible with the 8x50 electrical interface. So this is where the DD comes from. All the previous generations all had 4-wide electrical interfaces. This has 8-wide. How do we fit it in to make it work? So what we have here is...
just one question from a heat perspective.
Yeah.
If you compare it with 100G, how much more heat are these modules producing?
On a watt per gigabit, it's reducing, but
it's not 4 times the heat.
It's not 4 times the heat. So if you say 100 gig optics, it depends on the reach as well, right? So if you talk about 100 gig optics at about 3.5 watts, if you say 4 times that's 14 watts. So we're seeing most stuff come in around 14 watts. If you're going to try and do coherent optics and go thousands of kilometers, that's probably getting up to 17, 18, maybe even 20 watts. So the watts per gigabit is a good number. The absolute is the challenge, because what we were cooling previously at 3.5 watts, the form factor hasn't fundamentally changed, but we're now doing maybe 5 times the power in that. So how, from a system perspective, do we actually pull that off, right?
So your cooling budget goes up. That means you need more fans, more, let's say, heat pipes to get out.
There's quite a bit of innovation in that. Actually, and I'll just jump to that here. So let me just explain the connector, and then I'll explain the heat, if you're okay with that. So sure. The main thing on the connector is, if you've ever looked at the back of a QSFP module, you'll see a card edge with a bunch of contacts on it. All we did is created a second row of contacts, which you can see up in the top, that extends further out. And what happens there is when you plug that into your line system, into your host system, basically both rows, the PCB will go into your connector and both rows of contacts will engage. You can take an old QSFP 28, plug it into that same slot, and only, because it's a shorter card, only one of the rows will engage. So this gives you your backwards compatibility, right? And that's kind of the fundamental, I guess, breakthrough in concept of the time. And then the real challenge was, well, okay, we can go do that. Does it work from all the performance perspective? Can we cool it? Does the SI work? So back to your question on the thermals, the pictures on the side are kind of a cutout on the side. So this is looking at 2 QSFP DDs in a cage, in a system, and there's a lot of things we can do around this. A lot of it has to do with complexities of the cage design to let the air flow into it. We can attach heat sinks, so it's a flat top module, as you saw on the previous slide. It's a flat top module, so we can attach top riding heat sinks. So as it slides in, it touches the heat sink. So it's all down to the design of those heat sinks. You can put heat sinks inside the cage, in between them as well, to cool that lower one. You can put heat sinks up on the nose on the outside. And then it really comes down to system design, how you design that faceplate, how do the fans pulling the air through. And with all of this, we've demonstrated up to 20 watts, fill up a chassis, a line card with 20 watt modules in, and everything stays cool.
And I guess you tested this with the long-range modules to kind of
So
the extreme
the
factor.
long range, the ZR modules, which are the most power hungry, they're actually just coming out in real form, like this week, last week, next week. They're brand new. So what we do is we build up what we call thermal modules, where we take exactly the form factor and we fill it up with resistors and heat it all up, and we put the resistors in the same locations as where we know the heat source is going to be in the modules, and we do all our testing on that. So we're very confident, but yes, we haven't done that testing yet. Well, I don't have the results here today, but it's ongoing right now. So we don't have any concern, but they're all brand new. So we haven't, we'll be showing those results soon enough. What else did I want to say on this? I think I've said everything on the DD. Is there anything else before I switch to the next subtopic? Okay, so we were talking about the four things. We talked about silicon photonics. We talked about the single form factor. The next one is really speeding the optics up and getting it to 100 gig per lane. And this is a lot of the technology. This is silicon photonics really comes to the fore here. Is how do you get 100 gigabit on a single wavelength? And this is very important for the 400 gig, because then we can just do 4 wavelengths like we've done before. And it also allows us to cost reduce the 100 gigs. So right now, MSAs, it was started really, IEEE started some of the work, the MSAs picked it up, extended it, the IEEE is now taking it and qualifying all that. But really it's how do we go based on this 100 gig per lambda technology to develop 400 gig optics. So it's four channels, they could be wavelengths, they could be fibers. But when you look at it from a 400 gig perspective, that's sort of halving the number of wavelengths to what was originally thought we'd need of 8 wavelengths to go do this. And for 100 gig optics, it allows us to go and cost reduce 100 gig, which is in high volume today, which uses 4 lasers, and cost reduce that down to 1 laser in the package. So if you look at that, you can see sort of on the 100 gig stuff on the left, you'd have like a coarse WDM4, CWDM4 with 4 lasers. You can reduce that down to just 1 laser, and that's really going to drop the cost down. In the 400 gig space, you can go from what was 8 lasers, that's been specified by the IEEE, but you can reduce it down to 4 lasers, which is more in sync with what we as an industry know how to get to high volume. And more important, well, not more importantly, but also importantly, you can see that the wavelength range is relaxed. So when you have 4 lasers, you're able to relax the wavelength range. That lowers the costs quite a lot. That lowers the need to hermetically seal these things. It really makes things a lot easier to go do. And so when you have these building blocks, you can take one of these and stick it inside a QSFP28, and this would be something like you call 100 gig FR or 100 gig DR, the different reaches you can get. And this is a really low-cost way of doing 100 gig. Or you can take 4 of these and put them inside 400 gig DR4 or 400 gig FR4, and that's how you do your 400 gig. The beauty of silicon photonics to even drive the cost down more is you can actually take a single laser and split the light over those 4 fibers. And so you can have 1 laser inside this package, and it's driving 4 fibers independently. And then you can break those out. So this is one of the big applications of 400 gig optics is you can do breakouts, so dense 100 gig E.
I have one question regarding this. So I have seen this over several iterations that also then we had higher, let's say, demands on the fiber that we're using. Can we use, let's say, fiber standard that we had for our 100G implementations for that as well, or do we need new cables as well?
For single mode fiber, you won't have any issues. Where there's a subtle issue is, I'll talk about it. I got it back here. And when you're trying to do this one here, this 400 gig LR4, so when you're trying to do 10 kilometers, you're doing 100 gig per lambda, 10 kilometers, your dispersion is getting higher. If you go and look by what's specified by the standards for telecom fiber, which hasn't been sold for 25 years, you might run into some issues, right? The reality is no one really has that fiber and can't find the fiber, and you can't buy the fiber. But within the IEEE, and I'm in the middle of this because I chair both the MSA and the IEEE group, from a pure standards perspective, you can only say, yes, you can do 6 kilometers. So what the IEEE has done is they've said, okay, you can only do 6 kilometers, but we'll give you lost budget for 10. All right, so most people really don't need 10 kilometers anyway. They just want the higher loss budget so they can not worry about connectors and things. Within the MSA, we've relaxed that a bit, and we said, yeah, 10 kilometers is fine because we know no one really has this fiber.
Okay.
Okay. So the thing when you look forward and sort of forwards compatibility, the nice thing about this 100 gig per lambda technology is as the ASICs speed up, the SerDes go from 25 gig to 50 gig to 100 gig, you always want to stay ahead of the speed of the SerDes. So the last thing you want to do is have the speed of your SerDes and break out to lower speeds in the system. That's a costly way to do things. So for systems where we were based on 25 gig SerDes, which is basically everything that was in the 100 gig E domain, using 4x25 optics was fine because we had 4x25 coming off the ASIC going to 4x25 on the optics. As we move into systems now, which are based on 50 gig SerDes and 100 gig SerDes, you really want your optical lanes to be going faster. And so what we've just been talking about with the Cisco 8000, that's currently based on 50 gig SerDes. It's going to move to 100 gig SerDes like everyone else will. And so the moving to the 100 gig optical technology, you can put that in the systems today, regardless of your SerDes, but it'll be the longer term technology that you want to be using going forward. And I'm going to just speed up a little bit here because I want to give actually some time. So the fourth trend that's happening here is really putting the DWDM technology into the pluggables. This is expected to be this kind of shorter reach, hundreds of kilometers versus thousands of kilometers. This is expected to be 30% of the coherent market in the next few years. So this is a big trend that's going on right now. The OIF has gone and done the work. They said, let's go and develop an Ethernet optimized spec for pluggable coherent modules that can do about 120 kilometers. It will fit into the double density, it'll fit into OSP and CFP2. It'll just fit into all the pluggables. As we talked about, that is the challenge on the thermals, but we're confident that will go well. But the interesting thing here is it's going to be multi-vendor, and DWDM typically isn't multi-vendor. It's very proprietary, bookended, and this is kind of a big transition that's happening, which is why they're thinking this is going to move up to like 30% of the market. And so you see these kind of charts where you say, okay, there's all these different flavors out there, all these different reaches. The thing about once you get into DWDM technology is there's lots of knobs you can turn, so you can basically offset your distance and your speed, and these chipsets will all offer that. But at sort of the standard level, you're going to see sort of 400ZR, you can do about 120 kilometers at 400 gig. There's a couple of groups which are defining a version where we've got a better FEC. That allows you to probably triple the distance just using a higher grade FEC. But this stuff is getting a lot of attention right now. A lot of people excited about what they can do by putting the long haul in at the same time as a client. So finally, there's just a lot of work going on in the industry. There's MSAs, there's standards. It's just been crazy getting this already. But what we end up with now is basically solutions for everything from 3 meters of copper all the way up to hundreds of kilometers of fiber. All the different codes is anything sort of DR4 and down is all breakout capable, so it can break out into 50s or break out into hundreds, and everything above that is sort of single mode WDM type stuff. And just as looking ahead a little bit to your comment, what goes beyond 400 gigs? So we've already got a form factor being developed right now to do 800 gig. This is where we're going to try and put dense 400 gig in or dense 100 gig into that. Very confident, but once you have this going, you're going to have the ability to go from 100 gig QSFP28 all the way up to 400 gig, which is what we're talking about here in the double density, and then take that up into 800 gig, all backwards compatible all the way through. All right, so that's the end of what I wanted to say. I'll pass it over, but really the demand for 400 gig is here. Uniquely for this, we're going to see it all fit in the same form factor day one, and that's going to really accelerate the cost reductions as we're deploying, and we're in a very good position with our acquisitions, with our technology development, to deliver all of these optics to you.